Hello again, students. I have a feeling that this video is going to be rather lengthy because the lab that you're doing this week does not have written instructions, so you'll have to rely on this video, and I'll be as thorough as possible. I like to call this lab the Copernican Measurements Lab because at least some of these measurements, I believe, were first done by Copernicus. That's this guy on the left here, and others in his time. And then those measurements were later repeated and probably refined by this man over here, Johannes Kepler. I'm sure you've heard of him. He came along a little bit later during a time when it was very fashionable to wear an air filter around one's neck. And remember, this guy worked for Tycho Brahe, who definitely took a lot of really precise astronomical measurements, and Kepler is the one that interpreted them. So we've looked at some of the results already this semester, and I'm sure you have in your lecture class. And for this lab, we'll be concerned with the third law. Kepler's third law was the one that he discovered something like 10 years after the first two. And here's what it says. Only the planets that were known at the time are listed here. And believe it or not, you can actually make these measurements with the naked eye all the way out to Saturn. Saturn's actually up right now in the early, if you happen to be up at like 5 a.m. before the sun rises, I don't know why you'd want to do that to yourself, but look to the south and you can see Jupiter and Saturn near each other right now. You can check that in Stellarium if you don't believe me. Okay, so up here it says semi-major axis. For this lab, we're going to approximate the orbits as circular. And if an orbit is circular, then we could just talk about its radius. So this letter A would basically be the radius. And AU, I think you know that stands for Astronomical Unit. That's a unit of measurement much larger than the meter or the inch. If we were measuring the size of the orbit in inches, all of these numbers would be enormous, right? Like how far is the Earth from the sun in inches? That's a really big number. So instead, we choose a more convenient unit. We use Earth's distance from the sun as like the yardstick. So Earth would just be one unit from the sun. Now, down here it says Jupiter is 5.2 AU from the sun. That means that Jupiter is 5.2 as far from the sun as we are. That's why that's such a convenient unit. Now, the people at the time, I don't think they knew those distances to 4 digits. That's a little too much precision for the measurements back then. But they actually did have some sense of what these numbers were. They knew that Venus was roughly 72% as far from the sun as we are. And if you're anything like me, when I first started learning astronomy, I was curious how they could have known such things back then with so little technology and so little understanding really at the time also, because physics really hadn't even matured. This was before Newton. So not only did they know roughly the size of the orbits, they also knew how long it took the various planets to go around the sun. And again, we're going to use the most convenient unit possible. We're not going to measure periods in seconds because it takes Earth an awful lot of seconds to go around the sun. That's too big of a number. So we just use the Earth year, roughly 365 days. So it looks like it takes Saturn over 29 Earth years to go around the sun. And don't be confused by the word year. You are probably aware that the year is how long it takes the Earth to go around the sun. Well, Saturn's year is 29 Earth years. So I'm going to use the word year for the period of time it takes planet Earth to go around the sun. Okay, and here is what Kepler discovered. I have no idea how he discovered this because he didn't have a handheld calculator. He didn't have Excel. I'm sure he had an abacus, but it would have taken a lot of hand calculation to discover this. But check it out. If you take each of these numbers, the size of the orbit, which I'll call the radii, take this number, 0.387, and raise it to the third power. That means 0.38 times 0.38 times 0.38. Cube that, in other words, and you get this number. Then go ahead and take the period of the planet, how long it takes to go around the sun, square that number, and you get this number. What a coincidence. It's the same number. So the size of Mercury's orbit cubed is the same as the period of its orbit squared. Now, of course, that's only going to work if you measure the size of the orbit in astronomical units and you measure the period in years. Not only is it coincidental for Mercury, the same coincidence appears to be true for Venus. Take Venus's orbital size cube it, and that's the same number as if you take its period and square it. The fact that that continues all the way down the column tells us it cannot merely be a coincidence. There must be some reason why those numbers always come out the same. Now, they were only able to confirm, Kepler was only able to confirm that out to Saturn, because I don't think Kepler was aware of any planets beyond Saturn. But now we know that this law, if you will, also holds for Uranus, Neptune, pretty much anything in our solar system. It doesn't even have to be a planet. So the asteroid belt has chunks of rock in them. Those rocks also obey Kepler's third law. And it wasn't until Newton came along that somebody was able to offer an explanation. And that's what we call mechanics. That's one of the branches of physics. And it's really not that difficult to prove, believe it or not. All you would have to do is take an introductory class in physics here at Long Beach City College, and you could learn how to show why that's true. Okay, so how the heck did they make these measurements? And before I explain this picture, let's take a look at a simulation. Here we are back at the Nebraska Astronomy Applet Project website, our old favorite. And I really like this simulator, the Planetary Configurations Simulator. So you've got the sun at the center and two planetary orbits. You can think of one of them as Earth. So throughout this talk here, the blue planet is going to be planet Earth, and this will be some other planet. So right now we're looking at an inferior orbit. See how this planet's orbit is inside the Earth's orbit, which is out here. So we call that an inferior orbit. And we can watch how the Earth goes around as the inner planet goes around. And do you notice how it takes less time for the inner planet to orbit the sun than it does take for the Earth? That's really one of the pieces of information you can get out of Kepler's third law. Kepler's third law is more descriptive than just this statement, but it does say that the farther out the planet is, the longer it takes to go around the sun. Now, we need some terminology here. You're going to use it for this lab and for the next lab. Let me pause for a moment right here. Okay, imagine you are on planet Earth, and let's say it's right at sundown, so you can still see where the sun is. It's still setting, but the sky is getting dark enough that you can actually see some of the planets, namely the planets that are close to the sun. Maybe this is Venus. So imagine pointing the finger, take your pointer finger on your left hand and point your arm straight at Venus, and then point your pointer finger from your right hand at the sun. So your arms are outstretched with your fingers pointing at the sun and Venus, and your arms define a particular angle that you could easily see. You can visualize that angle. It's the angle between your arms. Of course, you could build some sort of instrument for measuring that, but that angle is called the elongation. It's the angle between the direction to the sun and the direction to the planet. So I'm going to hit start again. And of course, this isn't fast forward. It would take weeks for the planets to move like this, but you can see how as the planets orbit the sun, the elongation of, let's call it Venus, it changes. Right now it's closing up to 0, then it opens up again, gets to its maximum value. Now it's closing up again, going to the other side. So the elongation goes through a range of values, but you'll notice that it never opens up to 90. Let me pause it right here. Can you sense that this angle is never going to be 90? It can't be, because this planet is closer to the sun. That's really why. With an inferior orbit, that elongation will never open up past a certain maximum, as a matter of fact. Let me change the target planet to something outside. Okay, so now, again, the blue planet is Earth. Maybe this is some faraway planet like I've chosen Jupiter. And now watch the elongation. So it's opening up, opening up. Oh, it just passed 90. In fact, now it's all the way out to 180. So for a superior planet, the elongation, if you point your finger at the sun, you point your finger at Jupiter, you measure that angle, it can take all possible values. But let's go back to the inferior orbit. I'm just going to pick an arbitrary distance that's less than 1 AU. See here, I can set that. Actually, let's go with Venus. Do I want to do Venus? No. I can change it right here. There we go. Okay, 0.65. So I'm going to pause when the elongation reaches its maximum value. It's getting larger, 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 right? Here, do you see that? How the angle's never going to get any larger than that. Watch as I hit start, it'll start to shrink again. Now the angle's getting smaller. I'll let it go to the other side. Okay, now the planet's off to the east of the sun, right? Here again. Whoops, I missed it. Can I go back? No, I'll have to wait for the next one. I'm going to pause it again when it gets to its maximum value. And I'd like you to think about the relationship between the line from the Earth to the planet and the circle of the planet's orbit. So here it's coming up here. And this would happen over a period of months, I assume, right about here, almost. There we go. Okay, so I'm going to call this value the maximum elongation of this planet. Elongation is the angle between the line to the planet and the line to the sun. And notice that as I've freezed it right here, the line of sight from planet Earth to the planet that you're looking at, do you see that that line of sight is tangent to the circle of the planet's orbit? And that's the crucial fact that we need. The line of sight to the planet is tangent. And now we're prepared to actually look at how the distances to these inferior planets, or I should say the distances from the inferior planets to the sun, were actually measured back in Kepler's time. But first, let's simulate this also in Stellarium. Here we are in Stellarium, and I'm going to walk you through, I'll point out all of the keyboard shortcuts that I use, and she'll be doing this as well. I'm going to turn off the atmosphere with A, get rid of the ground with G, get rid of the cardinal signs, directions with Q, and I'd like to find Venus. So I'm going to hit F3, type in Venus, hit enter, zoom in. Now the camera is set up for a particular type of telescope. If I go down here, I can click on the telescope button and change the mount. If I want, I could hit the letter E for equatorial coordinate system, and I'm using the up and down arrows here. I'm zooming in and out. And I think what I'd like to do is track the sun. So I'll click on the sun and hit the space bar. Actually, no, for now, I'm going to click on Venus. Now check it out. When I click on Venus, there's a whole bunch of information that pops up about Venus. But down here, look at that. It says elongation 15 degrees. So that's telling us that between Venus and the sun right now is an angle of 15 degrees. And now I guess I'll track Venus. I'm going to tap L a couple times to speed up time. And do you see how Venus is moving closer to the sun? Look at the elongation over here. It's decreasing. It's on its way to 0. Now it's going past 0 to the other side. And again, if you look at see how the dates are flying by, it takes weeks and months for this to develop, but the elongation changes. And if I watch the elongation, I'm going to see that it never gets past right about there. See, it's about 45 right now. I'll speed up time again. Okay, it never got to 46. Venus has an inferior orbit around the sun. Its elongation never gets much past 45 degrees. So you'll be using that in the lab later. So how did they make those measurements back then? Did they get in a hot air balloon, because they didn't have space shuttles back then, get in a hot air balloon and go high above the surface of the Earth, way out into the solar system, to look down on the orbits of the planets? Because I just showed you that simulation where it's very easy to visualize the orbits. You have that bird's eye view. Well, obviously they didn't do that. First of all, I looked this up. They didn't have hot air balloons back in that time, so there was no way to get that high. And even if you could take a hot air balloon above the atmosphere, which you can't, the speeds at which they move mean that it would take hundreds of years to get high above the solar system. So of course that's not what they did. What they did was just make measurements of the night sky over a period of many months and infer things and use geometry. So let me show you how to determine the radius of an inner planet's orbit. I should have said an inferior planet's orbit. For this lab, you will not be measuring the outer radius because the trigonometry you need is a little more complicated. Okay, You just saw this in the web browser here, but now let's pause time at the moment where, so this is not Venus, but whatever this inner planet is, it's now at its maximum elongation. You can see that because let me get my laser pointer here, because the line from the Earth to the planet is tangent to the inner orbit. So the elongation will never get greater than that. And now I'd like to do this. I'm going to connect the line from the sun to the planet right here. There it is. And I will call this angle theta. This is the angle between the line to the planet, the line to the sun. In other words, that is the elongation, specifically the greatest elongation, because the greatest elongation happens when the line to the planet is tangent to the circle. So it's a fact from geometry that you may remember. See how this line is actually a radius of this circle? And a radius is always perpendicular to the tangent line at that point. Perpendicular. That means this is a right angle that we're talking about. And that means we're talking about a right triangle. Right here, this is a right triangle. This is the long side. Do you remember what that's called? That's the hypotenuse. And since we're dealing with the right triangle, we can use trigonometry. Remember sine, cosine, tangent, those pertain to right triangles. So the two relevant distances here. First of all, what is this distance from the Earth to the sun? Well, that's what we call the astronomical unit. And in that system of units, the distance is just 1. This is 1 AU. What we'd like to know is this distance. That's the whole idea here, is to figure out how far Venus is, for instance, from the sun. Now, even though they couldn't determine that distance in inches or feet, they could determine it in terms of the Earth-Sun distance. Because look at what we've got here. This side is opposite theta. You used the sine function in the lunar parallax lab, and we're going to use it again here because this is the side opposite theta, and this is the hypotenuse. And I'm using the letter A for the size of the orbit. So do you remember that the sine of an angle is the opposite side divided by the hypotenuse? Opposite side divided by hypotenuse. Maybe you've heard of SOHCAHTOA. The SO part is sine is opposite over hypotenuse. Okay, so the sine of theta should be A over 1. Well, 1, that's just the number 1. That's easy. But A is the number we'd like to know. That's the distance between the sun and the planet. So if we could just measure the angle, we could take the sine of that angle, and that would tell us what A is. Because A over 1, isn't that just A? So there it is. All we have to do is calculate the sine of the greatest elongation, and boom, we have the size of the orbit. How cool is that? I mean, it's so simple. You just have to watch the planet every night over a period of weeks, months, and then figure out what its greatest elongation is, and then compute the sine of that angle. So let me go back to Stellarium. Actually, I think what I'll do is, I'll simulate this in Stellarium. Okay, I'll do a demo with Mercury. Mercury is going to give you a little trouble. There's only 2 inferior planets, right? Mercury and Venus. You can get great results with this method using Venus. You won't get very good results using Mercury because Mercury's orbit is actually the most elliptical. It's really not a circle. So don't be disappointed by your results for Mercury. But I'm going to observe the elongation here, 16 degrees currently. I'll speed up time. And I'm going to observe the elongation. It's up to 25. Whoop. That didn't take long. So it's currently getting larger. I'm watching it, 17, 18, 19. Okay, it got to something like 19. Now, of course, you want to make your own observations. So don't choose the numbers that I'm using. I'll be checking to see that you made your own observations. I'm going to go with 18 as the greatest elongation here. Okay, so I pulled up a scientific calculator here. This is a great website, by the way, desmos.com. You can also just use Google's calculator. Hopefully you've got your own. But I'm going to calculate the sine of 18 degrees because that should give me the distance between Mercury and the sun in astronomical units. Okay, now make sure you're in degree mode, not radians. See how you can switch back and forth here? So I'm going to type, on this calculator, you have to put sine first. Then you put in the angle, and I guess I'll close the parentheses here and hit calculate. Oh, it did it for me. Okay, 0.309. I could just round that to 0.31. Let's compare that to the table. This is the table that I pulled up for Kepler's third law. And they're telling us that the actual semi-major axis for Mercury is 0.38. In fact, if you round it, it's 0.39. I had 0.31. Again, that's not great agreement, but that's because Mercury's orbit is rather elliptical. So you can just expect to get kind of crappy results for Mercury. Don't worry about it. Venus will come out better. And that's it. So you're only going to do that twice. Now, where do you put this? I have a sheet that you can fill out. Here it is. It's just one page here, and I'll point out right now, this is extra credit. Actually, nobody's going to do it. Nobody ever does this every semester because it's a little challenging. If you're interested, let me know. I'll send you some notes that somebody else prepared showing you how to do it. It's interesting, but don't feel obligated. This is really all you're going to fill out. So this might make it seem like this lab is trivial, but it's going to take you a while to actually collect the numbers. So let's see here. Here's the column for calculating the size of the orbit A. And notice I've highlighted these cells, and I've even put asterisks, I can't say that word, asterisks here to indicate that you can't even use this method for the outer planets. So you're only going to write down the greatest elongation for the two inner planets, Mercury and Venus. And then here is where you would use the sine function to find to find the size of the orbit, okay? So I'll be looking to see that you have your own values here. So that the part of the lab that I've described thus far, it's just these 4 cells. That's it. All this other stuff you're going to do with a different method. Okay, so that's it for determining the size of the orbit. Now let's talk about measuring how long it takes a planet to go around the sun. Okay. Now, there are 2 different methods here. You're going to do both. One works for inferior orbits, one works for superior orbits. Let's start with the superior orbit. I'm going to go with a planet like Mars. So here's Earth in blue, and Mars is out here at a superior orbit. Let me hide the elongation angle for now. And first, let's talk about some vocabulary. Okay, I'm going to pause this at some key places. Right about here is good. I think I can adjust this. Yeah. Okay. Do you see how Earth, Sun, and the outer planet, they all fall on a line? In fact, if you were on Earth looking towards the sun, wouldn't you be looking in the same direction as the outer planet? In other words, they would look like they were in the same direction. Let me simulate that in Stellarium. Here we are back in Stellarium. Let me find Mars. Okay, now Mars is nowhere near the sun at the moment. Where is the sun? It's way over here. So I'm going to use the bracket buttons to skip ahead a week at a time. There we go. Now Mars is much closer to the sun. Let me zoom in here. Okay, it's getting real close. So that screenshot that I showed you in the simulation there would correspond to a moment like this. Do you see how when you look towards Mars, you're looking in the same direction as the sun? And that is what's called a conjunction. You know, conjunction is, whoops, what did I just do? I just lost it, but you saw it. That's when 2 things are in the same place in the sky. They're conjoined in some sense. And there are actually 2 types of conjunctions. Notice here, they're also telling us it's conjunction. Now, are there 2 types of conjunction? No, I'm thinking of an inferior orbit. So there's really only 1 type of conjunction. Great, so we don't have to worry about that. Okay, let's just make sure that we can understand what's going on here. Right about here is another, let me back up. This is another event called an opposition. because you'd have to look in the opposite direction to see the planet than you would to look at the sun. Or you could say that the elongation is at 180 degrees. So at opposition, the elongation is 180. If you pointed each finger, one at the sun, one at the planet, your arms would be in opposite directions. And I believe that is actually the configuration that we're going to use. Now here comes the most challenging thing conceptually about this lab. You really kind of need to understand this in order to use the formula that I'm going to give you. I'm going to hit start here. And because Mars is considerably further from the sun than we are, actually not Mars, let me go with Jupiter. Yeah. Earth is going to make a complete orbit, and during that time, Jupiter will not have moved by very much. So right now, this is opposition, right? Down here it says opposition. You have to look this way to see the sun. You have to look this way to see Jupiter. That is opposition. And what I'm going to do is hit start and let the system evolve until Jupiter is back at opposition. So I'll pause it at the next opposition and watch carefully. So Earth is going through an entire year, and it's going to pass a year, and then right there, they're back at opposition. So what did the Earth do between those two oppositions? Earth made a full orbit, that's 1 year, and then it did a little extra, maybe a couple months extra, because it takes 12 months to go around. So this was something like 14, 15 months. 1 full year for the Earth and a little bit extra, and we're back at opposition. Now, there's a very important term that you need to know that you'll be using here. That amount of time for Jupiter is called a synodic period. Synodic period. It's the time between two successive oppositions. Jupiter would have been next to the sun, and then it would have left the sun as seen from Earth, and then it would have joined up with the sun again. So the synodic period is the time between two successive oppositions. In fact, I can put everything back where it was. And down here, there's a little graphic that helps you visualize that. And I take that back because Jupiter is completely in the opposite direction. But it's from one opposition to the next. And you'll notice that Jupiter really doesn't move that far during that one opposition. So that's the synodic period of Jupiter. But there's another type of period. It's actually the one that you normally think of. The amount of time it actually takes. So now I'm going to speed up the animation here. Watch how long it takes to Jupiter to go all the way around the sun once. So the synodic period just went by already. It takes much longer for Jupiter to actually orbit. And I think that's what, 12 years? So by the time Jupiter gets all the way back here, that's called the sidereal period of the planet Jupiter. So the sidereal period is what you would normally think of as the period. It's how long it takes the planet to do a full orbit of the sun. There's the synodic period for Jupiter, that's the time between oppositions, and the sidereal period, two distinct things. And the sidereal period is what you cannot observe directly. Right? People back then did not have the luxury of going way up into space in a spaceship, looking down and waiting 13 years to watch Jupiter go around. That's not possible. But what you can do directly is to measure the synodic period. And I can show you that in Stellarium. Let me find Mars, since I've been using that as an example. Okay, I want to put Mars at opposition. Well, that's tough to visualize because as soon as Mars gets really far from the sun, it would disappear from the screen. So you can't see the sun and Mars at the same time when they're at opposition. So what I could do is use the elongation here. When they're at opposition, the elongation is 180. So I'm tapping the right bracket to go ahead a week at a time, and I'm watching the elongation here. Sorry, right here. And I'm waiting for it to get all the way up to 180. That's going to take a while. And it never actually seemed to get there when I was tapping 1 week at a time. So now I'm using L, JK and L to adjust time. Okay, And I don't quite understand that. It went up to like 178, but it never actually reached 180. I forget why that is. I think it's because the orbits are tilted. In any case, you could do that to find two oppositions, like get it close to 180, write down the date, and then fast forward time until you get to the next opposition. But it turns out that you don't actually have to use oppositions to do this, to find the synodic period. It works just as well if you use conjunctions. So I'm going to repeat this again later in the video, but please just use two successive conjunctions for an outer planet. I'll show you what I mean. Right now, I've set the configuration up so that Mars is at conjunction with the sun. If you're here on the blue planet, Earth, looking towards the sun, you would be looking in the same direction as Mars. So they would be right next to each other in the sky. That's conjunction. And I'm going to hit the animation and just keep watching until it's back at conjunction. Okay, that's opposition right about here. That was pretty good. They're back at conjunction again. And you can see that down here. It says sun and planet. They're in the same part of the sky. So the time between two successive conjunctions is also the synodic period. It doesn't matter which you use, two successive oppositions or two successive conjunctions. You should use conjunctions because that's something you can actually simulate in Stellarium. So I will repeat, use the time between two successive conjunctions in Stellarium to find the synodic period for an outer planet. And I'll demonstrate that real quick. Okay, so let me use Mars once again, and I'll search for a conjunction. Now I'm going to be checking that the dates of your conjunctions are not the dates that I'm using right now. I need to make sure that you did the work yourself. So it happens all the time. Just fast forward, go in 100 years into the future, 1,000 years, whatever, and find a conjunction between the planet, each outer planet that you're doing, and the sun. Again, I recommend using the brackets, left and right brackets, to go ahead a week at a time and get closer. Otherwise, you're going to give yourself a seizure with the light spinning around here. Okay, that's getting real close. That's already pretty good, but now I'll tap L a couple times to get it even closer. K is pause. That's the quick. You can also do all that down here with the time controls here, but I like the keyboard shortcuts. Okay, and now the cursor is telling me that it's practically in the middle of the sun. That's as good as I'm going to get. That's really close to conjunction. So this is very important. You don't want to waste your own time here. Once you've found a conjunction, go down here and note the date. I don't think I need the time. That's more precise than I need. But definitely write down the date. Actually, if you don't mind, squeeze in this time right here, UTC minus 8 hours. Because depending on what time it is, depending on what time zone you're in, the dates could get goofed up. So please include all this stuff if you can fit it into the cell. But for sure, I need the date. Then fast forward time. I would go ahead in time. You can use the brackets again until the very next, excuse me. You're going to go ahead in time until the very next conjunction. Don't skip a conjunction. You have to pick the very next one and also write down that date. I'll show you that in the paper. Okay, so I need the dates of your conjunction. And remember, the time between those two conjunctions, that is the synodic period for the outer planet. Here's the handout. So right now, again, I'm talking about the outer planets. There are 1, 2, 3 outer planets, superior orbits. I'm talking about Mars right now. You would write down date 1. If you can, please squeeze in the time and the time zone, the UTC minus whatever. Put that for date 1 and date 2. And now you need the time between those two dates. That will be the synodic period. And let me show you how to do that. I'm going to go to the I'm going to go to a web browser, and you could do this by hand. You could figure out the number of days between two dates by hand using a calculator, but you can also go to a website and get that done. So I'm going to show you what I'm talking about. So all I typed in here was calculate time between two dates, and a whole bunch of websites came up. I'll go with this one. And I'm just going to pull two dates out of the air here. Let's say I'd like to know how many days pass between, I'll go with July 1st of this year, for instance, 2020, and I don't know, August 13th of 2063. Okay, and it's up to me whether I want to include the end date in the calculation. I think you would want to do that. So we're going to count the days between them. Here it is, 15,749. All right, that's the number we need, because we need to convert that into the number of years that pass between those two dates. Why? Because in this exercise, we're measuring time in Earth years in order to confirm Kepler's third law. So first get the number of days and then convert it to years. I'll show you how to do that. 15,749. Okay, I'll use PowerPoint here. I think, what was it? 15,749 days. And then I'm going to multiply that by a conversion factor to convert that into years. So I go into the equation here, need a fraction bar, and let me put a little X to indicate multiplication, times, okay, there is 1 year for every, and you might as well use the more precise figure, 365 1/4. And I'll use my hand calculator next to me here, 15,749 divided by, so you'll divide by 365, and that comes out to 43 years. Do you see how that works? Whoops, I had to put the word days here. This is a conversion factor. The days cancel top and bottom, and we get an answer out in years. Okay, so you can use Google to get the number of days between successive conjunctions of your outer planet, and then just take that number of days divided by 365 to get the number of years, and that's what you can put into the handout. So that's going to go right here. So your the number of days is not going to appear in this handout. I mean, you can squeeze it in there if you want to show me what you did, but I definitely need to see the two dates, and then here is where you write the number in years, so after you've already done the conversion. And that way I can check in Stellarium, I can check your work and make sure that this number is accurate. That's the synodic period now. That doesn't actually tell you how long it takes the planet to go around the sun. What it tells you is the duration between two successive conjunctions. That's something that a person could actually measure if they went out every night and observed the angle between a planet and the sun, and waited for conjunctions. And now it's time to talk about how to convert the synodic period into sidereal period, because it's the sidereal period, P, which actually appears in Kepler's third law. It's that period that's squared. Okay, so this is also going to be a challenging part of the lab, explaining how that's done. First, the vocabulary. I will be using capital S for synodic period, S for synodic. And remember, the actual time it takes for the planet to go around the sun, that's called the sidereal period. For the Earth, the sidereal period is the year, 1 year. And I'll use P for sidereal period because P is kind of like the true period. The sidereal period is more like the true period. And then capital E is going to stand for Earth's sidereal period. We can't call that P because P is reserved for the planet's sidereal period. Okay, so we have 3 different letters. Make sure you understand what they stand for. And now let's go back to the, so even though you're going to use two successive conjunctions in order to find the synodic period, I'm going to explain the following method using opposition because it's easier. So here's a diagram of opposition. Sun is to the left, planets to the right. Superior planet. And here we are at the next opposition. And I did my best in PowerPoint to trace out the path taken by each planet Earth and the outer planet, between those two successive oppositions. So the Earth started out right here. It made a full orbit. It took a year to do that. And then it went a little extra until it was at opposition again with, or until the outer planet was at opposition again. So the red line shows the path traced out by the Earth from one opposition of the outer planet to the next opposition. And the outer planet only went this far because the outer planet is not moving as quickly. That's one thing that Kepler's third law tells us. Okay, so the amount of time that is passed during the tracing out of these red paths is what we call the Synodic Period. That's how long it took to do this, an amount of time called the Synodic Period. And I'm calling it opposition to opposition, but remember, you can just go from conjunction to conjunction in Stellarium. And here is the key reasoning here. Once they're at opposition again, I've drawn a line through the three heavenly bodies, and here's a particular angle here. And I'll try to word this as clearly as possible. If you don't get this, try rewatching it a couple times. I'm going to look at a ratio. I want to ask the amount of time it takes Jupiter, let's just call this Jupiter. The amount of time it takes Jupiter to go from here to here. How does that compare to the amount of time it takes Jupiter to go all the way around the sun? That's the ratio that I'm talking about right now. The amount of time it takes Jupiter to go from here to here compared to the amount of time it would take Jupiter to go all the way around the sun. Well, we have names for those amounts of time. You just saw that by definition, the amount of time it takes Jupiter to go from one opposition to the next, that's called the Synodic Period. That's what we can actually measure by making observations of the night sky. And the number we'd like to know is how long it takes Jupiter to go all the way around. That's the sidereal period. So the ratio that I'm talking about is really S compared to P. Amount of time it takes to go here, just that wedge, compared to the denominator, which is how long it takes to go all the way around. And that the crucial part of the reasoning now is we can say that that comparison, that ratio, should be the same as a similar ratio for Earth. So let's go back to Earth now. How long does it take the Earth to go from here to here? That's the same little wedge compared to how long it takes the Earth to go around once. It's the same ratio. So we need to figure out how to express this same ratio in terms of Earth times, Earth quantities. Okay, so here it is. Well, the amount of time it takes to go around once, that's easy. That's just E, the Earth year. In other words, 1. But this amount of time is a little trickier. So remember, the Earth started here at the first opposition and then went all the way around. It passed its starting point and got to here. That whole amount of time is called the Synodic Period, right? Remember the squiggly a couple slides ago? The amount of time it took Earth to do this whole thing is the Synodic Period. But I'm interested in just the amount of time it took Earth to go the little bit extra. So if we take the Synodic Period of Jupiter and then subtract just 1 year, subtract how long it takes to go around the circle once, that will give us the difference. In other words, the leftover time, how much extra time it takes Earth to go from here to there. That's it. So the amount of time it takes to go from here to here for the Earth is just the full Synodic Period minus 1 year. And that's what I've got right here. So the numerator here, Synodic Period minus the Earth year, that's the amount of time it takes to do the little bit extra. And then, of course, E for Earth year is the amount of time it takes Earth to go around once. And what I'm saying is that comparison is the same, whether you use that line of thought for Earth or use that line of thought for Jupiter. I'm equating two ratios. Really what I'm doing here is writing two ways of expressing, or I'm expressing in two ways this angle compared to the full circle, 360 degrees. So you don't actually have to understand how I got this formula to use it. I hope that you do, but you do need to understand what these letters mean and how to use this formula. So I've rewritten it here. And now let's recognize that we're going to be measuring time not in seconds or hours, but in Earth years. This formula is true regardless of the units that you use. But now let's evaluate this for Earth years as our unit of time. Well, what is E in Earth years? It's just 1. The sidereal period of Earth is just 1 if you measure time in Earth years. But before I do that, it looks like I've done some algebra here. I cross multiplied. So I put the E over here and the P over there. That's how I get to this formula. Now I'm going to evaluate this for E equals 1, right? S times 1 is just S. And what I've done here is I've distributed. Remember from algebra, this would be P times S minus P times E. So here's P times S. And of course, P times E is now P times 1, which is just P. What are we doing with this formula? The whole idea is to find P. We want, if you're Copernicus or Kepler back in the 1600s, 1500s, you're trying to determine the sidereal period. How long does it actually take Jupiter to go around? So let's solve this for P in terms of S. So what I did here was I moved the P to the other side and I had a PS. What did I do here? No, I'm sorry. What I did was factor out P. Take this expression, factor out P, and you get this. So I factored out the P and then I just flipped the two sides of the equation. And then the last step to solve for P, of course, would be to divide by S minus 1. Again, if you don't follow all the algebra, that's okay. You just need to know how to use the formula. And there it is. Pretty simple formula. If you have measured the synodic period already in Stellarium using the time between conjunctions, then you just use this formula to find the period P. Now, it's up to you to make sure that you're doing order of operations correctly. So I'm going to check your numbers. I'm going to check that the number that you wrote down for the sidereal period matches the rest of your work. But what you can do is at least check your value against a table of values online to confirm that you've done it correctly. If the sidereal period is supposed to be 30 years and you got 1,000,000 years, something is wrong. Check your order of operations. So you got to make sure that you're using the calculator correctly. Okay, but it's as simple as that. And I will point out that because you're subtracting 1 here, you're going to end up with a small number in the denominator sometimes. And that means you have to be really careful. Make your measurement of S as carefully as possible. If you're off by even a few days, that could potentially screw up your value pretty bad, your value for the sidereal period, P. Okay? So now we need to go back and, because there's a very similar formula for inner planets. Remember, this formula is for superior orbits. There's a different formula for inferior orbits. I know there's a lot going on in this video. That's why you're going to have to rewatch it. So you're using the sine function to find the distance between the sun and the planets only for the inner orbits. And then when it comes to the sidereal period, you're going to use this other method. And there's one formula for the outer planets. There's another formula for the inferior orbits. Let me talk about that now. I'm going to take the target planet now and make it an inferior planet like Venus. So Earth is on the outside, and now Venus is on the inside. And let's try the conjunction method. Right now, do you see how when you look towards the sun, you would also be looking towards the planet Venus? So they would appear next to each other in the sky. That's a conjunction. But they're calling it not just a conjunction, but a superior conjunction. So let me slow down the animation here. Notice how even though they're in the same direction, Venus is on the opposite side from the sun. It's far away. I'll hit play here and watch the way the next conjunction looks. It's coming up. It's coming up right about here. Now, when you look towards Venus, again, it's in the same direction as the sun. You can see that down here. In the sky, they look like they're practically on top of each other. That's also a conjunction. But this is a different type of conjunction because Venus, instead of being over here, which is called a superior conjunction, Venus is near to the Earth. In fact, that's as close as Venus is going to get to the Earth. That's called an inferior conjunction. They're telling you that right here. So the synodic period is actually the time between two successive conjunctions of the same type. And that means in Stellarium, you have to skip a conjunction. So you need to either go from inferior to inferior conjunction or superior to superior conjunction. It doesn't matter which one you do. Let's take a look at that in Stellarium. I'll go to the search bar and type in Venus, for example. Okay, Venus is clearly not at conjunction. I'll tap L a couple times. Oh, let me go back the other way. I'm sorry, not L. I'm tapping left bracket to go a week at a time. Okay, they're pretty close there. Notice they're not actually on top of each other, but they're aligned vertically with the blue lines. Remember, you might have to adjust the way the camera is mounted. See, that way they don't look like they're at conjunction. This is a little clearer. Now I'm going to use L. Oh, let me go backwards. So I'll use J, back in time, pause with K. That's pretty good. It doesn't need to be much better than that. That's definitely a conjunction. Now, how close is Venus? You don't really need to know that to do the lab, but if you look at the distance here, this is the distance from Earth, and they say 0.29 basically AU. That means it's closer to us than we are to the sun because we're 1 AU from the sun. And that tells us that Venus is actually at inferior conjunction. Venus is between. You can't tell that by looking at it here, but Venus is actually closer to you than the sun is over here. Okay, so that means, well, what I need to do now in order to measure the synodic period, you would write down the date, try to squeeze the time in there as well, but definitely write down the date in the handout. And now you're going to go to the next conjunction of the same type, which means you're going to have to skip the next conjunction. You have to do every other conjunction. So let me zoom out, and I'm going to go forward in time by tapping right bracket 1 week at a time. And I think Venus is getting closer there. Yep. So this is a little tedious, but hey, it's way less tedious than doing it in real life. Venus is now back at conjunction, but don't be fooled. I went past it a little bit there. This is not the conjunction we're interested in. If I look at the distance to Venus, now it's at 1.7 AU from the Earth. That's on the other side of the sun. So this is the superior conjunction. I need to skip this and wait for the next inferior conjunction. Again, it doesn't matter if you do superior to superior or inferior to inferior. Just make sure you skip one. It's taking a while here. Hurry up, Venus. There we go. That's pretty good. I overshot. You get the idea. When you actually do it, you want to make these line up a little better. Get the best results you can. You know, your results will come out better the more careful you are. All right, so they're lined up pretty well there vertically. All right, and then I would write down this date. This is the date of my next consecutive conjunction of the same type. Okay, so let me just repeat that advice because this is one of the confusing things here. You can use the same method for determining the synodic period, whether you're doing a superior planet or an inferior planet. But this distinction is this. For a superior planet, do not skip conjunctions. Just do one conjunction and the very next conjunction. Do not skip a conjunction for superior planets. When you do the inferior planets, you do need to skip a conjunction. You need to do 2 consecutive conjunctions of the same type. Last thing we need to do is develop the formula for converting from synodic period to sidereal period, the appropriate formula for inferior orbits. You've already got the formula here for superior orbits. All right, here's the distinction. For a superior planet, Earth is the one close to the sun. For an inferior planet, the other planet is the one that's close to the sun. Okay, so I already showed you where this formula came from. And to get the next formula, let's go back to a previous starting point. Remember, I started here with the superior planet. But check it out. When you look at the graphic, these two graphics, don't we just have the roles of Earth and the other planet reversed? For superior planet, Earth is inside. For inferior planet, Earth is outside. So what we can do actually is go back to this formula right here and just flip the letters. Because now E, the sidereal period of the Earth, would correspond to P, the sidereal period of the other planet. Does that make sense? It's a clever way of getting the other formula without having to start from scratch. We just interchange the roles of E and P because we've switched their roles in the diagram. Now, it's not so obvious that S, the synodic period, doesn't matter either way. I mean, if you're waiting, like if you're going from conjunction to conjunction for Jupiter, that's to measure the synodic period. Well, when you're on Earth looking at Jupiter and it lines up with the sun, that means that if you were on Jupiter looking at Earth, it would also line up with the sun. You'd have conjunctions either way. So S doesn't change when you reverse the roles. Okay, so if I switch E and P, I get this formula here. And then again, evaluate E at 1. Earth's sidereal period in years is just the number 1. And so we're just left with S minus P. And then I'm interested in finding P. I want to know P, the sidereal period of the inferior planet. So it looks like I moved the P over to the other side and then factored it out. And then the last thing here would be to divide by S plus 1. And there it is. In fact, it's the same formula as the formula for the superior planet. The only difference is there's a plus sign instead of a minus sign. So here are the formulas. I think you should write those down so you don't have to come back to this video, but otherwise you could just pause it at this frame and use these formulas when you get to that part of the lab. Again, make sure you're using order of operations correctly. I'll be looking at your dates, and I may check them in Stellarium. I may put them into the calculator to find the years and check that your periods that they match the numbers that you wrote down. And then you can fill in this column. So this column here, every one of these cells will be filled in with your own work. So it may take you a little while to do all of this in Stellarium, but once you get the hang of it, it'll go more quickly. This will all be your work. This will all be your work. Same thing with these columns. These are the dates that you will have written down in Stellarium. Now, don't forget, for the last 3 rows, you do not have to skip a conjunction. For the first 2 rows, you do have to skip a conjunction because those are inferior planets. So you're going to fill out this whole block yourself. Now, if we go back to the determination of A, remember, that method only works for inferior planets. So only these 2 numbers will be numbers that you found yourself. What you can do for these is just look them up. Yeah, I said shaded cells for extra credit. You're welcome to just look these up in a table and write them in. But everything else needs to be your work, and I'll be looking for that. So here, right here, the column of periods squared, you can actually determine the periods yourself for all of them in Stellarium. So I'll be checking that this number here, for instance, is really the square of the number you wrote here, that this number here is the square of the number that you wrote here. The squares of the periods need to be from your own work. And at least for the top 2 planets, the inferior planets, these numbers, A cubed, they need to be the cube of the numbers you wrote over here. Use your values for A. If I look over here and find that this A cubed is something totally different from this number here cubed, it means that you didn't do the lab correctly. You just looked up A cubed in a table, and that's pointless. The point of the exercise here is to simulate these measurements. Okay. Now, of course, for the outer planets, since you can't actually determine A using that method, you would have to look those up, and that means you can look these up as well. So only for the shaded boxes should you be writing down numbers that you did not yourself calculate. All right. So now you realize why this lab is just a single chart here. It's going to take you a while to collect this data, but that's all you have to do. And I'm hoping that at the end, you take some satisfaction in observing that the square of the period does equal the cube of the semi-major axis or the radius. And those were all those numbers were gathered from simulated measurements in Stellarium, measurements you could have done theoretically in real life. And again, don't expect great results for Mercury. Your semi-major axis A is not going to come out great. It might if you're lucky, because since it's an elliptical orbit, everything's always kind of changing. But don't be upset if these don't come out great. Venus should look good. You should get pretty good agreement between P squared and A cubed for Venus. If you're really stuck on any of the instructions, shoot me an email. You've got a week to do this. Arguably, this is one of the more challenging labs because of all the stuff you have to do in Stellarium.